Today, we're going to be starting our final module of the class, which is open channel flow. So this is going to be a departure from what we've been looking at previously. So let's just first give a quick overview of open channel flow, what we're going to be talking about, why you will need to know about open channel flow as a civil engineer, where you'll be encountering it, and what the differences are between open channel flow and pressurized pipe flow. So up until now in this class, we've talked about flow in pressurized pipe systems. So these are pressure-driven pipe systems designed to supply potable water. So these include things like water distribution systems, premise plumbing, plumbing that you might find at a water treatment plant. From now on until the end of the class, we're going to be talking about flow in open channels. So these typically correspond to gravity-driven systems that are associated with drainage. So this can include either natural drainage, so i.e. river networks, or designed drainage systems, so in particular, stormwater systems. So why do you need to know about open channel flow and where are you going to encounter it? Probably the place that most of you are going to encounter open channel flow as a civil engineer is in the design of stormwater systems or urban drainage systems. So regardless of what specialization you are focusing on as a civil engineer, whether it's transportation, structures, geotech, at some point you will encounter drainage as an issue in your design project. So typically when you go to work at an engineering firm, one of the first things they're going to put you on is design of drainage systems. So drainage from, for instance, if you're working on a housing development, you may need to figure out the drainage from the housing development and what systems are needed to accommodate that drainage. So it's a very common type of engineering problem that you will encounter at some point during your career. So let's just talk about a few applications of open channel flow that you will likely encounter. So within the design of urban drainage systems, you'll often find that drainage is facilitated through stormwater channels. We'll talk a bit about how to design these channels to convey a specified discharge. These structures you've probably seen before. What are these structures designed for? Culverts. Right. So if you didn't have structures like culverts, your channel would wash out every time that there's a major storm event, which is not what you want to have happen. So culverts also need to be designed to accommodate a given discharge while avoiding overtopping. We'll be talking about those hydraulic relations when we talk about design of open channels and culverts. We have street and highway drainage. This is something you will probably be working on if you do any kind of development work, like working on a housing development. You need to design gutters to convey an appropriate amount of water while avoiding spread onto the roadway. And simultaneously, you need to design curb inlets to intercept an appropriate amount of water to ensure that you're not overcharging your gutter system. Those curb inlets eventually flow to storm sewers, which are designed to convey water underneath the surface. So these may function as either pressurized systems or open channel systems, depending on how full they are. You'll need to understand the hydraulics for both. So they can be either small storm sewer systems or very large ones. So on the right, that's an image of the TARP system in Chicago, which is one of the biggest storm tunnels in the US. So when we're studying open channel flow, it doesn't only correspond to design infrastructure, it's also going to be applicable to natural systems as well. So the same equations that I'm going to be talking about for modeling fluid flow in designed open channel systems also apply to natural streams. So our learning objectives for the next section, we're going to first describe the characteristics of open channel flow and its various classifications. So specifically, I want to talk about how open channel flow differs from pressurized pipe flow, which we've been looking at up until this point. How are they similar? How are they different? I'm going to define a couple different common types of open channel flow that you'll encounter. So uniform flow. We'll talk about the normal depth, uniform flow, uniform discharge, and hydraulic efficiency. We'll apply energy principles to open channel flow. So taking the concepts that we learned from pressurized systems and applying those to open channel flow to analyze those systems in a similar way. We'll talk about rapidly varied flow and hydraulic jumps. And we'll also show how to model gradually varied flow, which is common if you're doing large-scale hydraulic design, so things like dams and weirs and impoundments. All right, are there any questions on where we are going so far? Okay, so this is going to take up the rest of the course. We're going to be using a lot of the same knowledge from the first part of the course, but just applied to different kinds of problems. Any questions before I move on? Nope. Okay, so let's talk a bit about open channel flow. And first, I want to just give some context for open channel flow and how it is both similar to and differs from pressurized pipe flow that we've been talking about up until this point. So in many ways, open channel flow and pipe flow are very similar. They're similar in that they're going to be governed by the same basic physical equations. So they're both going to still be governed by things like conservation of mass, conservation of momentum, conservation of energy, and many of the other mathematical tools that we've developed for pressurized flow are also going to apply directly to open channel flow, namely frictional losses we are going to compute in the same way. So I'll write frictional loss formulations. These are going to be very similar for open channel flow. Generally, over open channel flow, we're going to be using Manning's equation, although it is possible to use the other frictional loss equations as well. But overall, open channel flow and pressurized pipe flow are not different in terms of the physical equations and mathematical tools that we're going to apply. There's just going to be details about each case that changes how we analyze them. And in many ways, open channel flow is a bit more complicated because of those details. So first, let's talk about this first subject, conservation of mass. And let's look at pressurized pipe flow and open channel flow and see how conservation of mass is the same and how it's different for pipe flow and open channel flow. First, let's take a look at pipe flow. Let's say we have a pipe. And let's say the pipe is flowing completely full of water. This blue line represents the water in the pipe, and the pipe is completely full. You have some flow rate coming in, which I'll call Q in. And you have some flow rate coming out, which I'll call Q out. We can also draw a cross section of the same pipe just to show that the pipe is filling completely full. So this is our cross section here. Okay, and when we applied continuity or conservation of mass to a pressurized pipe, what did it tell us in plain English? What was the general rule that we could follow for continuity in a pipe system? How do the flow in and flow out relate to each other? They're the same. So Q in is equal to Q out. We also know that that implies that the velocity in times the cross-sectional area in is equal to the velocity out times the cross-sectional area out. So if we take a look at just an infinitesimal element of this pipe, I'm going to say this is some infinitesimal element with width dx. We found the following relation for both the change in volume within that element and the flux through that element. So we have that dq by dx is equal to 0, and dA by dt is equal to 0. So let's talk about what each of these terms means, just as a refresher. So what does dA by dt equals 0 imply again?
Cross-sectional area of the flow of the water.
Yeah, the cross-sectional area of the flow doesn't change over time, which implies that the volume of water in our control volume doesn't change over time. So I'll say this means that the rate of change of volume is constant. Sorry, is 0. And what does this term here imply? Yeah, so it means that the volume flux in is equal to the volume flux out. So the flow in is equal to the flow out. So I'll write the volume flux into that infinitesimal element is equal to the volume flux out. So in many ways, this simplified our life considerably. We could always assume that the flow in was equal to the flow out for a given pipe section. Let's look at the case of open channel flow. So here is the bottom of our channel. Here is the surface of the water. So open channel flow is characterized by a free water surface. We can specify some control volume within the open channel. And we may have some flow rate into that control volume, Q in, and some flow rate out, Q out. We also can take a look at the cross-section of this open channel. So let's say we have a trapezoidal channel like we showed on the slides earlier. So this is what our cross-section will look like. Here's the channel bottom and sides. And then we may have some water level in the channel. Bless you. Bless you. So in this case, we don't necessarily have that the flow in has to equal the flow out at any given time. So it is possible, for instance, to have a flood wave that's coming in. Let's say maybe it's moving like this. And as that flood wave enters this control volume, the flow rate in will increase. The flow rate out may not increase by the same amount at any given time. And the volume within that control volume, the volume of water within the control volume, may change over time. So for the case of open channel flow, if the system is not steady state, Q in is not necessarily equal to Q out. And we have to use the full expression for our continuity equation, dq by dt plus dA by dt sorry, this should be dq by dx plus dA by dt is equal to 0. So in other words, what does this expression for continuity imply? We talked about it a bit earlier when we first derived continuity. We've been ignoring the full expression up until now. So dq by dx means the flow out minus the flow in. dA by dt means the rate of change of volume or cross-sectional area within the control volume. So what does this equation here mean in plain English? Yes, so the rate of change of volume within your control volume is equal to the flow in minus the flow out. So that's the more general case. That's the more general expression for conservation of mass for open channel systems. That is the case that adheres if you're not working under steady state conditions. So remember that fact. There's also another difference that we can see here just by looking at these diagrams that we're going to need to deal with. So look at the shape of the cross-section for pipe flow versus open channel flow. And you'll notice that for pipe flow, the shape of that cross-section is always constant. For open channel flow, that's not necessarily going to be the case. So let's take a look at the differences between these two types of flow in terms of the hydraulic geometry. So for pipe flow, we had it easy. We have some circular pipe. We know that it's always flowing full. We have some diameter associated with this pipe. And thus, if we need to know the cross-sectional area, we know that the cross-sectional area of the water is always equal to what in this case, if we know the diameter? What's the equation for our cross-sectional area? Right, so pi over 4 times d squared. So our area will always be a function of the diameter of the pipe. Similarly, our wetted perimeter, the perimeter that is in contact with the water, will be pi times d, right? The circumference of the circle. So for pipe flow, both of these hydraulic geometries are constant. Let's take a look at the case of open channel flow. So let's say we have a trapezoidal channel. We have some water level in the channel. And let's say that water level, we'll call it H1. And at some point, that water level may rise to H2, a different height. And you'll notice that both of these expressions for our hydraulic geometries will change with respect to the height of the water in the channel. So the cross-sectional area in general will be some function f of h. I'll get into how to specify these functions later, but they come from geometry. And similarly, the wetted perimeter will be some other function, which I'll call g of h. So for pipe flow, we had it easy in that the hydraulic geometry was always constant. For open channel flow, those hydraulic geometries, which will be used both in our expressions for continuity and in the expressions for our frictional losses, those hydraulic geometries change as the depth of water changes. So it makes things a bit more complicated. Any questions so far? Let's talk a bit about what hydraulic geometries are going to be something we need to know. So the most relevant hydraulic geometries are the following. Let's say we have a trapezoidal channel. And we have some water surface. And we will say that the depth of water in the channel is given by H. So this is the depth of water above the channel bottom. So there are a couple of key hydraulic geometries that we're going to need to know. The first is the cross-sectional area of flow. So that is this entire area here. So we have A of H. This is the cross-sectional area of flow. And you can see it's going to be a function of the depth of water in the channel, as well as parameters that define the geometry of the channel itself. So we have A of H, that's the cross-sectional area of flow. Another key parameter that we're going to need to know, specifically for computing the frictional losses, is the wetted perimeter. So that refers to the perimeter that is in contact with the water. So that would be this perimeter here. It does not include the top. It only includes the perimeter that is in contact with the water. So P of H, this is our wetted perimeter. And again, this is a function of the depth of water in the channel. A third important hydraulic geometry we're going to need to know is the top width, T of H. So this is going to come into play when we start talking about the energy equation and different types of flow. We'll be talking about subcritical and supercritical flow. The top width is an important parameter for differentiating between those two types of flow. And then there's a final parameter that we need to know. Does anyone remember how the hydraulic radius is defined? Okay, very good. So the hydraulic radius is equal to the cross-sectional area divided by the wetted perimeter. And again, this is going to be something we're going to be using a lot when we're computing frictional losses in open channels. So the hydraulic radius is another important hydraulic geometry we're going to need to know. And it is, again, a function of the depth of water. Okay, any questions on these hydraulic geometries? No. So there's two different cases that we'll consider when looking at hydraulic geometries. The first is the case of prismatic channels. So these are characteristic of human-built channels. So they consist of basically regular geometries that are extruded in space. So you may have, for instance, a rectangular channel. Let me, my line tool here. You may have a rectangular channel. You may have a triangular channel. You may have some sort of semicircular channel. And very commonly, you will have a trapezoidal channel. You'll see why that's the case on one of the homework problems. So these these types of channels have hydraulic geometries that can be defined by analytical functions. So in general, they're easier to work with. In addition to prismatic channels, we also have natural channels. And these are characterized by irregular hydraulic geometries. So a common shape you might see for a natural channel might look something like this. You'll have some kind of floodplain region. Then as you get into the channel proper, it'll go down steeply like this, and then come back up, and you might see something like this. So you will have some water level in the channel. And these channels, generally, you won't find a analytical form for the hydraulic geometries, but you'll have to approximate them numerically. So how might you go about determining things like the cross-sectional area or wetted perimeter for a natural channel like this? How do you think it's done in practice?
That certain points and then maybe do a straight line fit between each of the 2 points.
Yeah, that's pretty much exactly right. So you basically just break the channel into vertical partitions like this. And then you create interpolated line segments representing the bottom of the channel for each one. And then from this, you can get, you compute the hydraulic geometries for each of these segments. And then from that, you can get the overall hydraulic geometry for the entire channel. So this is how it would be done in a computer program like HEC RAS, which they'll be working with on one of the labs later on in class. Okay, any questions on hydraulic geometry so far? Okay, let's go through an example of computing functions for different channel types. So hydraulic geometries for different channel types. So first, let's look at a rectangular channel and let's compute the cross-sectional area as a function of the depth, the wetted perimeter as a function of the depth, the top width as a function of the depth, and the hydraulic radius as a function of the depth. Again, this is for a rectangular channel. With some bottom width B as in Bravo, and some water depth H as in hotel. So let's draw out our channel. So again, we have some water depth H, some bottom width B. All right, first, cross-sectional area as a function of H. How can we express the cross-sectional area of flow as a function of the depth H? B times H, very good. So it's just the area of this rectangle here, which will be bottom width B times H. All right, what about the wetted perimeter P as a function of H? 2H plus B. Is it 2H plus B or 2H plus 2B? Just one, yes. So it's 2H plus B. So remember, when we're talking about the wetted perimeter, we do not count the top of the water. We only count the perimeter that is in contact with the surface of the channel. Okay, what about the top width T? It's just B because that's a rectangle. And then the hydraulic radius is equal to A over P. So that's going to be BH over 2H plus B. So for a rectangular channel, we can specify these hydraulic geometries pretty easily. Let's look at a slightly tougher case. So let's do the same thing. For a triangular channel. With side slopes. Bless you. Side slopes M is in mountain, and these are specified in terms of horizontal to vertical. So let me draw that out. Let me try to make this an even triangle here. Okay, I'll just do it like this. So we have some water level in our triangular channel. The depth of water is equal to H as in hotel. The side slopes are M in the horizontal direction. So M is in mountain to 1 in the vertical direction. Again, this is M to 1. So the run is M, the rise is 1. All right, so first, how can we compute the cross-sectional area as a function of the depth? Probably the easiest thing to do is to break this up into two right triangles. And then we can multiply H by the base of this right triangle here. So we have that 1/2 of the cross-sectional area is equal to 1/2 base times height. So what is an expression for this base B in terms of the variables that we know? We don't know T, but good guess. What is the base in terms of the side slope and the depth? M times H, very good. So note that based on the side slope here, for every 1 unit we move in the vertical direction, we move over M as in mountain in the horizontal direction. So if we move over H in the vertical direction, that means we move M times H in the horizontal direction. So the base of this triangle is M times H. So this will give us 1/2 of quantity M as in mountain times H as in hotel times H as in hotel. And if we multiply this by 2, we get the entire cross-sectional area, which is equal to M as in mountain times H squared. All right, any questions on how I got the cross-sectional area there? All right, what about the wetted perimeter? So again, we're talking about this line here, this line segment here, plus this line segment here. What's an expression for just the length of this line segment here? Sorry? Tangent. So we don't know the angle explicitly. We could go that route, but there's an easier way. Yeah. Very good. So it's the hypotenuse of this right triangle. So the one leg is h, the other leg is mh. So we can take the square root of h plus mh squared. Sorry, h squared plus mh squared. So the wetted perimeter is going to be equal to 2, because we have two hypotenuses, times the square root of h squared plus b squared. Remember that b is equal to m as in mountain times h. So we're going to end up with 2 times the square root of h squared plus m squared h squared. Note that we can factor out that h squared. So this would be 2 times the square root of h squared times quantity 1 plus m squared. And we can factor that h squared out of the square root. So we end up with 2 times h times the square root of 1 plus m as in mountain squared. Okay, so this is just from the Pythagorean theorem. All right, what about the top width? 2b, which is equal to 2 times m times h. So the top width here, this is equal to 2 times m times h. And then the hydraulic radius, it's just equal to the cross-sectional area divided by the wetted perimeter. If we carry out that division, we get m times h divided by 2 times the square root of 1 plus m as in mountain squared. Okay, any questions on how I got these hydraulic geometries? So there are other types of prismatic channels. I have for you a reference table up on Canvas. So if you go to Canvas Pages Reference, there is a table for hydraulic geometries that'll give the equations for different hydraulic geometries for different channel types. So we have rectangular, triangular. Trapezoidal is just a combination of a rectangle and a triangle, but you have equations here for your convenience. Just note that it uses different notation here. So instead of using h, it's using y as the depth of the water. So just be mindful of that. Also note that hydraulic depth is not the same thing as hydraulic radius. We don't really care about hydraulic depth for this class. So just be mindful that they are not the same thing. Okay, any questions? All right. So let's keep moving then. So we talked about how continuity differs between pipe flow and open channel flow. Let's take a look at the force and energy balances for pipe and open channel flow and how those balances differ. So we're going to be looking at force and energy balances. Let's take a look at pipe flow first. So let's say we have a pipe, we're at some angle to the horizontal. Let's say this angle here is given by theta. We have a length of pipe, which I'll call delta x. All right, so what are the forces acting on the fluid in the pipe? So let me just draw that fluid. What are the forces acting on the fluid in the pipe? There were three main ones we talked about. Pressure. So there will be a pressure force acting on both the upstream and downstream end. So this pressure force is given by P1A1 at the upstream end and P2A2 at the downstream end. Okay, what other forces are acting in the direction of flow? Sorry? Gravity. So we have the force of gravity acting on the fluid. So in the vertical direction, this would be given by mg. In the direction of flow, it'll be given by mg times the bottom slope, assuming that sine theta is approximately equal to the bottom slope. So we have we have the pressure force, the gravitational force, and what is our third force that we need to account for? Friction. Very good. So there will be a frictional force that is acting opposite to the direction of flow. I'll call this F sub F, and this is equal to the mean shear stress times the wetted parameter times the length of the pipe. So those are the three main forces acting on the fluid in the pipe. We can specify our momentum balance or our momentum equation. And remember, to accomplish this, we applied Newton's second law to our control volume of fluid. We have that the sum of forces is equal to the time rate of change of momentum. So if we equate the time rate of change of momentum to the sum of forces, we get the following expression for our momentum equation. We have dq by dt plus dqu by dx plus the acceleration due to gravity times the cross-sectional area times 1 over the specific weight times dp dx, so that's the pressure gradient, minus the bottom slope plus the friction slope is equal to 0. So that was our momentum equation. If we integrate this momentum equation over some length delta x, what do we get? What equation do we get if we integrate the momentum equation over some length delta x? Sorry? Energy equation, right? That's where the energy equation comes from. So the equation you've been using throughout the entire class, it is the integrated form of this momentum equation. We take this entire expression and we integrate it from some upstream point to some downstream point. From that, we get the energy equation. And our energy equation was given by P1 over gamma plus D1 plus U1 squared over 2G is equal to P2 over gamma plus Z2 plus U2 squared over 2G plus head losses from 1 to 2. So remember where the energy equation comes from. I may ask this on a test at some point. Okay, so these are our momentum balance, our force balance, and our energy balance for pressurized pipe flow. Let's take a look at the case of open channel flow. So we'll have an open channel. Again, this is a sloped open channel So just like with the pipe, we have some angle with the horizontal of theta. We have some water level in the channel. And we have, we can draw a control volume, just like we did for the mass balance. Okay, and now let's think about what forces are going to be acting on the water for the case of open channel flow. So is there a frictional force acting on the water? Yes, so there will be a frictional force induced by the bottom of the channel. So there will be a frictional force that is formulated much in the same way as for pressurized pipe flow. Okay, is there a gravitational force acting on the water? Yes, so we will also have a gravitational force that acts in the exact same way. So we have mg is the gravitational force in the vertical direction. In the direction of flow, it'll be just as before, mg times the bottom slope, where sine theta is approximately equal to the bottom slope. Okay, what about pressure? Is there a pressure force acting on our control volume? So there is an atmospheric pressure acting on the top. What about on the sides? Who thinks yes? Who thinks no? So there's no pressure acting on the sides of the control volume. Yes. So you may remember back to fluid mechanics that there is a pressure exerted just by the weight of the water. So you may have computed this for a submerged object. Much in the same way, there is a pressure force that is exerted by the weight of the water on the sides of this control volume. So you may remember back in fluid mechanics, drawing these triangles, right? So there is a force that's being exerted just by the weight of the water. And we call this the hydrostatic force that is exerted by the hydrostatic pressure. So what is the equation that you can use to determine the hydrostatic pressure as a function of the depth? Rho GH, very good. So the hydrostatic pressure is equal to rho times G times H. So rho times G is the specific weight. So the hydrostatic pressure is equal to the specific weight times the depth of the water. Similarly, we have that the depth of the water is equal to P over gamma. So let's take this formulation here and see how we can adapt our existing momentum equation and our existing energy equation for the case of open channel flow. So you'll note that here we have, for the pressure force term, 1 over gamma times dp dx. So for the case of open channel flow, this just becomes dh dx. What is the physical meaning of dh dx? It's the slope of the water surface. So the slope of the water surface determines our pressure force term in our momentum balance. Okay, what about for the energy equation? What does this term here get replaced by? What does our pressure head term get replaced by? So it was P over gamma in our pressurized pipe flow case. For the case of open channel flow, what will it become? Just H, right? Just the depth of the water. So this will be H1, and this will be H2. So when we're applying the energy equation for open channel flow, generally that pressure head term will be expressed just as the depth of the water itself. Any questions on the force balance for open channel flow? So again, the same, but a little bit different. Okay, with the remaining time in class, I want to go over a couple different classifications of different types of open channel flow that we'll be looking at. So this will kind of set the stage for the major topics that we'll be talking about for the remainder of the class, the different cases of open channel flow. So let's talk about classifications of open channel flow. So first, let's talk about different classifications temporally. So there's two main cases. We think about open channel flow and how it either varies or does not vary over time. So the first and most general case is unsteady flow. And this is the case where the depth and velocity of water, so the depth and velocity of flow vary over time. So a quick visualization of what that might look like. Let's say we have flow in an open channel. And maybe we have a dam break at the upstream end of the channel. And that dam break produces a flood wave. So we might have something like this. So at t equals 0, we'll have a flood wave located at the upstream end of the channel. As time progresses, that flood wave moves downstream, make it a little steeper. So this is t equals 1. And then as time progresses further, that flood wave will progress even further downstream and get steeper. So the depth is changing with time at different locations in the channel. And also the velocity is going to change as well. So underneath this flood wave, you might have a larger velocity and a smaller velocity upstream and downstream of the wave. So unsteady flow is the most general case. To analyze fully unsteady flow, you need to apply the full momentum and continuity equations. In general, it's something that's going to be too complex to look at in this class. If you go to graduate school, you may study unsteady flow, particularly if you take a class in computational fluid mechanics. The case that we'll be looking at in this class is steady flow. So let's say we have flow in an open channel. So for the case of steady flow, we have that the depth and velocity are constant in time. So I'll just write R constant. Actually, I'll write in time, because they're not necessarily constant in space. So for example, we might have something like this. Okay, so we have flow in an open channel that may transition to a smaller depth. Maybe there's some change in the geometry here. You might have a slower velocity at this upstream part, and then as the depth of the water goes down, this velocity increases. And this is the case for all time. So this is for t equals 0, equals 1, equals 2, and so on. So for steady flow, you can have the depth and velocity changing in space, but in time they are constant. That's the case we'll be looking at in this class. Any questions on this classification? Okay, and the other classification I want to talk about is how flow may vary or not vary in space. And these apply specifically for steady flow. So we have a couple different important classifications. The first is uniform flow. So we'll be looking at this case extensively over the next couple of weeks. And uniform flow is basically the simplest possible case we have, where the water depth and velocity, so the depth and velocity remain the same throughout the length of the channel. So let's see what that looks like visually. So we have some open channel. We have that the depth and velocity are the same throughout the entire length of the channel. So for this case, only one thing can happen. We have a water surface that is parallel to the bottom, because everywhere the depth needs to be the same. So we have that H1 at the upstream end is equal to H2 at the downstream end. So for uniform flow, the only thing that can happen is that the water surface is parallel to the bottom slope of the channel. So we'll be talking about this case pretty extensively over the next couple of weeks. It's an important case for design in particular. The second classification I want to talk about is gradually varied flow. So this is something we'll be looking at more towards the end of the class, but it's another important case that you will need to know. So for the case of gradually varied flow, water depth and velocity vary gradually over the length of the channel. So one common case for gradually varied flow is the case of a backwater, often caused by an impoundment or some other obstruction in the stream. So let's say we have an open channel that terminates in a dam. So the water surface in this case will vary along the length of the channel. You'll have a shallower depth at the upstream end, and then as you approach the dam, you're going to get a larger depth like this. So this is called a backwater. And within the channel, the velocity is also going to vary. So kind of at this impounded point, you'll have a much slower velocity. Upstream, you'll have a larger velocity. So we'll be looking at this case towards the end of class. The final case we'll be talking about, and one that you will be looking at in your next lab, is rapidly varied flow. So in this case, water depth and velocity vary rapidly over the length of the channel. kind of the canonical example of rapidly varied flow is the hydraulic jump. So you will have some water coming in fast with a low depth. It encounters a transition where it suddenly jumps up to a higher depth with a slower velocity. So this will be called a hydraulic jump. And you will be looking at this shortly in your next lab. So these are the main cases that we'll be talking about in this class. For the next couple of weeks, we'll be talking about uniform flow. After that, we'll cover rapidly varied flow, particularly hydraulic jumps. And then towards the final part of the class, we'll be talking about how we can simulate gradually varied flow. Often these different regimes can all work together in a channel system. So to give an example, you might have a channel that looks like this. It's not time to go yet. So you might have a channel that looks like this. We have some sort of complicated system like this. So here we might have a sluice gate that is holding back water from some reservoir. So as the water passes under the sluice gate, you might get rapidly varied flow that transitions into uniform flow. At some point, it'll undergo a hydraulic jump. It'll jump up. Okay, it will discharge over a weir, which we'll also be talking about. Okay, that flow will go over the weir, enter the channel. It may encounter a change in the bottom slope, so it may change like this. Okay, it may go back to uniform flow as it travels over the length. And then as you encounter another change in the bottom slope, it will give a backwater, which is a case of gradually varied flow. So let's just label each of these transitions. So right here, we'll have rapidly varied flow. For this distance here until we encounter the hydraulic jump, this will be uniform flow. As we go through the hydraulic jump, we'll get rapidly varied flow again. We'll have uniform flow again up until it hits this weir, at which point we will get rapidly varied flow again. As we are moving over this transition, we might have gradually varied flow. At the point of the transition, at the change in the bottom slope, we might get rapidly varied flow. As it travels over this constant bottom slope, it'll tend towards uniform flow. And then as we approach this break in the slope, we may get gradually varied flow again. So typically in a real channel system, you'll have all of these different types of flow. So they'll need to know all of them, although I'll tell you about when particular cases adhere and when we can apply certain types of analysis for our channel design. Okay, with that, that's all I have for you today. So have a great spring break, and I'm holding office hours today at 11:30 if you have questions on the homework. Okay, thank you.